So for the rest of this chapter, we're going to talk about properties that solutions have that are a little bit different than pure substances. And the properties that we're going to talk about are called colligative properties. The reason why they're called colligative is because they depend on the concentration of the solute, but not its identity. So, it doesn't matter if you have a sugar solution or a salt solution or whatever the salt is, the concentration is the only thing that will affect these properties, not their identity. All right, so these properties include the vapor pressure reduction, freezing point depression, boiling point elevation, and osmotic pressure changes. There's different pressure depending on the concentration. All right, so let's talk about each of those. So vapor pressure lowering. All right, so if you have a solution that has a non-volatile solute, so say a water with sugar dissolved or something like that, so a non-volatile solute, the vapor pressure will go down from that compared to the pure solvent or pure water. Again, it's a colligative property, and so it depends on the concentration. So the higher the concentration, the lower the vapor pressure will be. It actually is proportional to the concentration in terms of mole fraction, and this is called Raoult's law. So Raoult's law says that the vapor pressure of a solution containing a non-electrolyte, that means one that does not dissolve into ions, non-volatile, meaning that the solute does not Okay, so for example, let's say the vapor pressure of water, pure water at 20 degrees Celsius is 17.5 torr. Now, if you keep the temperature constant and you add glucose to the water, again, because of vapor pressure lowering, the vapor pressure of this solution should be lower than 17.5. So in the problem, they're telling you that the mole fraction of glucose is 0.2. So that means that the mole fraction of water is 0.8. So the vapor pressure of the solution is just 0.8 times the 17.5, which gives you 14 torr is the vapor pressure of the solution. So again, because if the mole fraction of the solute increases, it becomes more concentrated, the mole fraction of the solvent will go down, and so you'll be multiplying by a smaller number, and so the pressure of the solution, the vapor pressure of the solution will go down. All right, so here's another example. Glycerin is a non-volatile non-electrolyte. So calculate the vapor pressure at 25 degrees of a solution made by adding 65 grams of glycerin to 500 grams of water. And note that the vapor pressure of pure water at 25 degrees is 23.8 torr. So we're going to use Raoult's law that the vapor pressure of the solution will equal the mole fraction of the solvent times the pure vapor pressure of the solvent. So the first thing we need to do is we need to find the mole fraction of the water since we're not given it. So to find the mole fraction, we need to have the total moles and the moles of each of them. Well, we need the moles of the water and the total moles. So if we first take 65 grams of glycerin and convert that to moles, it's 0.706 moles. 500 grams of water is 27.8 moles. So if we find the mole fraction of water, it's 27.8 divided by the total 27.8 plus 0.708, which gives us a mole fraction of 0.975. And so the vapor pressure will be 0.975 times 23.8, which is 23.2 torr. So it lowers it just a little bit. All right, a little bit beyond what we're going to be talking about. What if your solute is volatile, meaning that it easily vaporizes? Then each component will contribute to the vapor pressure, and so it's not quite so straightforward. This is Raoult's law for a volatile solute. The vapor pressure of the solution is equal to the pure vapor pressure of the solvent times the mole fraction of the solvent plus the pure vapor pressure of the solute times the mole fraction of the solute. And so the vapor pressure depends on both the pressure of the solvent and the solute. We're not going to be doing any of these problems. It's much harder to separate these kind of things, but this would be like, say, a mixture of alcohol and water. The vapor pressure is going to be different depending on the concentration, but you can't, you have to know the partial pressure of both the solute and the solvent. Again, we're not going to be doing a problem with these. You can probably, if you go on and do some organic chemistry, you'll do some of these. All right, so the second colligative property that we're going to talk about is the boiling point elevation. So just like the name implies, the boiling point of a pure, a boiling point of a solution will be higher than the boiling point of the pure solvent. Remember that the normal boiling point of a liquid is the temperature at which its vapor pressure equals 1 atmosphere. Because vapor pressure is reduced, like we just talked about, the vapor pressure of a solution is lower. And so because the vapor pressure is lower, it's going to take a little bit more energy to reach 1 atmosphere. And so it will boil at just a little bit higher temperature. So the boiling point of the solution is higher than that of the pure solvent, and it's called the boiling point elevation. The boiling point elevation symbol is delta TB. So delta is the change in the boiling point. And it's a colligative property because if you increase the concentration, that difference in boiling point will also increase. So delta TB is equal to the boiling point of the solution minus the boiling point of the pure solvent. So how much above the normal boiling point will this boiling point of the solution be? Here's just a picture of it. So if you look at the phase diagram of say a pure a pure substance, and then you add some non-volatile solute. Well, notice that the vapor pressure, so that on the right hand side, because the liquid now will because the vapor pressure lowers to the blue line to the purple line, what you notice is that the purple line now crosses the 1 atmosphere line a little bit higher temperature than original. And so that's why so the delta TB is the difference between the blue line at 1 atmosphere and the purple line at 1 atmosphere on the boiling point, right? So the vapor pressure, the right hand line. We'll talk about the freezing point in just a second. Okay, so the boiling point elevation, delta TB, is equal to Kb, which is a constant that will depend on the solvent that we're using, and little m is the molality of the solution. So again, the delta T, the amount that the boiling point elevates, is directly related to the concentration in molality. And since temperature's changing, that's why we use molality instead of molarity. So we're using molality. And remember, what is molality? Moles of solute divided by kilograms of solvent. Again, Kb is a constant that will either be given to you or you can look up, and it will depend on the solvent that you're talking about. Here is a chart of the different Kb and also Kf, which we'll talk about in just a second. So for example, if your solvent is acetic acid, your boiling, the KB is 3.08 degrees Celsius per molal, and the boiling point is 118.5. So the delta T will be that much above 118.5. Water, you can see on the bottom, of course, the boiling point of water is 100 degrees Celsius, and the KB is 0.512. So that would be the constant you would use in the equation. Ethanol has a boiling point of 78.3 and a KB of 1.07. So, well, we'll talk about it in a second, but be careful to use the correct boiling point for the solvent that you're talking about. Okay, so let's talk a little bit about the freezing point depression. So we'll do an example of a boiling point elevation and freezing point depression because they're very similar in just a minute. All right, so when a solution freezes, what happens is the crystals of pure solvent actually separate out, and so the solute particles won't stay soluble in the solid phase. So actually, the part of the phase diagram that represents the vapor pressure of the solvent won't change. But because the triple point is lowered, as you saw on that chart, which I'll show you just again in a second, because the triple point is lowered because of the vapor pressure of the solution, meaning the liquid to vapor line gets lowered, the triple point gets lowered, and so the freezing point is also lowered. So the freezing point of a solution is always lower than the freezing point of the pure solvent. Here's the graph again. So we saw from the boiling point that the pure solvent vapor pressure goes down. So that purple line comes down from the original vapor pressure, which lowers the triple point over here to the left. The blue triple point now comes down to the lower purple dot. And so the delta TF, meaning the change in freezing point, lowers as well. And so again, the blue freezing point of the pure solvent, and then the solution will come down to the left. And so we have delta TF, which the freezing point will lower for a solution. So what we have here is if you have a solution, then both the freezing point is lower and the boiling point is higher. So what you've done is you've really extended the liquid state of this of the solvent by adding something in. And just for some examples, this is why we put salt on ice in the winter, because what it does is it lowers the freezing point of the ice, and so it will less likely freeze because the freezing point is lower. It's also why you put antifreeze in your car. You're putting a non-volatile, non-electrolyte in your, well, the electrolyte we'll talk about later, but you're putting a non-volatile substance inside your water in your car. It lowers the freezing point, so it will freeze at a much lower temperature than pure water. So that's good. It'll stay a liquid at much cooler temperatures. But also, so antifreeze is a little bit of a misnomer because it's also anti-boiling, because it will also raise the boiling point. So, you know, when you add antifreeze to your car, you're making that liquid so from maybe -10 to 110 or something like that, rather than 0 to 100. So these are some examples that you're familiar with. In a very similar way to the boiling point, the freezing point depression is given the symbol delta TF. Again, it's a colligative property, and so the more concentrated the solution, the lower the freezing point. Delta TF is just the temperature of the freezing point of the pure solvent minus the temperature of the freezing point temperature of the solution. Delta TF is T minus TF pure minus TF solution. And so in the same way that the boiling point depression is related to concentration, the freezing point depression is also proportional to the concentration in molality, because again, we're changing temperature. So delta TF equals KF, which again is a constant for the solvent that you're talking about, times the molality. KF is called the freezing point depression constant, and it depends on the solvent, and we saw that on the previous slide and I think on the next slide. Yeah, Yes, again here, so for water, we saw the boiling point was 100 and the boiling point constant was 0.512. The freezing point for water, of course, is 0 degrees Celsius, and the KF is 1.858. And so if we're using alcohol, which you can't do a freezing point for alcohol, ethanol. If you're using cyclohexane, which I believe if you're doing this lab, the freezing point depression lab, we use cyclohexane and we add an unknown to it. The boiling point, well, no, we're not doing the boiling point. The freezing point of cyclohexane is 6.55 and the KF is 20. So that's an example that we do in lab if you haven't done it already. Okay, so let's do a quick example. We have an aqueous solution which is 0.22 molal in glucose. What are the boiling point and freezing point for this solution? So this one's fairly straightforward because we've already given you the molality. Of course, you might not get a problem that's straightforward. They may give you grams or liters or whatever, in which case we already know from earlier in this chapter how to find the molality. So you might get a problem like that, but once you find the molality, you can use it in the problem like we'll see. So the boiling point, so we can look up, since we're talking about water, we can look up Kb for water is 0.512 degrees Celsius per molal, and the Kf for water is 1.86 degrees Celsius per molal. So we know those values, or we can look them up. All right, the boiling point elevation and freezing point depression are equal to the equations that we just saw. So boiling point elevation, delta TB equals Kb times m. So 0.512 degrees Celsius per molal times 0.22 molal. So the molals cancel and we get 0.11 degrees Celsius. So that don't forget that that is not the boiling point. Obviously, it's probably it's easy to note that, but it's the boiling point elevation. That's how much higher the boiling point is from the original boiling point. So to find the actual boiling point, we have to add it to the boiling point of the pure solvent, which in this case is water. So 100 plus 0.11 gives me 100.11 degrees Celsius. We can do the same thing for the freezing point. So delta TF equals KF times the molality, which is 1.86 times 0.22, which gives me 0.41 degrees Celsius. Again, this is not the freezing point, but this is the freezing point depression. And so to find the freezing point, we have to subtract the freezing point depression from the actual freezing point, which, since it's water, is 0 degrees Celsius, minus 0.41, so it's a negative 0.41 degrees Celsius. Again, be really careful that you use the correct K value depending on the solvent. If you were using ethanol, you would use a different value, or if you were using cyclohexane, you would use a different value. And then also, when you add it to the actual boiling point, make sure you use the correct boiling point for the solvent in question, or the correct freezing point for the solvent in question. Don't always use 100 and 0 because it will change depending on what you're dissolving it in. Okay. The fourth colligative property is that there's a change in osmotic pressure from a pure solvent. So before I talk about osmotic pressure, I'm going to just briefly talk about what osmosis is. You probably talk a little bit about it if you've taken some biology, but just do a little refresher. So if you have something called a semi-permeable membrane, which is the orange dashed line on the picture, it's a membrane that allows solvent molecules, like very small molecules, to pass through, but does not allow the larger solute particles to pass through. So it's semi-permeable, only lets some things through. So osmosis is the phenomenon of water, the solvent, water or whatever the solvent is, flowing through the membrane to kind of bring concentration or equalize concentration on both sides of the membrane. So if you look on the left-hand side, you can see that obviously inside the little tube where the membrane is attached is a concentrated sugar solution. It's not the same concentration as the pure water on the outside. So what happens, osmosis occurs to try to dilute that solution down. So because the glucose can't come down, the only thing that can happen is that water will flow into the more concentrated solution. So you can see here that actually some water can go back and forth, but more water will go into that little bell-shaped area than come out, and so it's attempting to dilute down the solution. You can see on the right hand side that the water has passed through and diluted it down, and then what happened is that the height of the solution has raised up. So we've added more water and the height. So you can see that that height is labeled pi in this picture. The height that from the original height to the top of the to where it raised to. So it's diluted it down, and the volume, or the volume has increased, and so the column of water or column of solution has risen, and that's called osmosis. So that will naturally happen. Now, what is osmotic pressure? All right, so osmotic pressure is a colligative property, and it's equal to the pressure that will just stop osmosis. So if you think about the picture on the previous slide, if you were able to somehow put some pressure on that column of solution to not allow it to rise, even though osmosis was occurring, you would have to literally push it. Either once osmosis has happened, you would have to literally push it back down, or put pressure on it to stop it from happening. The amount of pressure that you need is equal to the osmotic pressure. And of course, the more concentrated that solution is, the higher that column would rise, and the more pressure you have to put on it to stop it from happening. So the osmotic pressure is given the symbol pi. It's a capital pi, and it's not equal to 3.14. Don't get that confused. That's just the value of lowercase pi when talking about trigonometry or anything. Anyway, the osmotic pressure, capital Pi, is related to the molar concentration of the solute. So pi equals mRT. M, of course, is molarity, so that's moles per liter. R is the ideal gas law constant, which is 0.0821 liters atmospheres per mole Kelvin. And T would be the temperature in Kelvin. So again, the pi, the amount of pressure, the osmotic pressure, is directly related to the concentration in molarity, since at a constant temperature. So let's say we have a 1 molar aqueous sugar solution or glucose solution. The osmotic pressure at 25 degrees would be equal to 1 mole per liter times 0.0821 liter atmosphere per mole Kelvin times the temperature in Kelvin at 25 degrees would be 298 Kelvin. So notice that the Kelvin cancels, the moles cancel, the liter cancel, and your answer will be in atmospheres, and osmotic pressure will be 24.5 atmospheres. Okay, so as we'll see, osmotic pressure is a very important concept, especially in biological systems. Now, if two solutions have identical osmotic pressure and we separate those two solutions by a semi-permeable membrane, then no osmosis will occur. There may be some water molecules moving back and forth, but there won't be a net gain on either side. So these will be, no osmosis will occur, and these two solutions are considered isotonic to each other. If one of the solution has a lower osmotic pressure, it would be hypotonic with respect to the other. If one solution has a higher osmotic pressure, it will be hypertonic with respect to the other. So, like I said, osmosis is important in many biological processes, and that's because a cell is considered a cell is surrounded by a semi-permeable membrane, so it allows some smaller molecules like water to move in and out, whereas it keeps the bigger molecules or bigger substances inside the cell. So it's very important that if you have a cell that has a particular osmotic pressure, that the solutions surrounding the cell, like for example your blood, must also be isotonic for the cell to survive. So because you don't want osmosis to occur into or out of the cell. If you put a cell into a solution that's hypertonic to the cell, meaning it would have a higher concentration, then water will move out of the cell to try to dilute down the hypertonic solution it's in. The water will move out of the cell. This dehydrates the cell, and the cell will shrivel, which is called crenation. So that would be what happened if you drink some salt water. If you're stranded on an island and you drink some salt water because you have no fresh water, eventually you would dehydrate yourself. All the water will literally move out of your cells. If you put a cell into a solution that's hypotonic to the cell, then this time the lower concentration outside the water will flow into the cell, and eventually the cell will burst, which is called hemolysis if it's a blood cell. All right, so let's do an example. The average osmotic pressure of blood is 7.7 atmospheres. So that means your blood cell has an osmotic pressure of 7.7 atmospheres. So if you're in the hospital and you want to get intravenous glucose, what should the concentration of that glucose be to make it isotonic with blood? And it's at 37 degrees Celsius, which is body temperature. So remember, for osmotic pressure, pi equals mRT. And now we know pi, and we're trying to find the concentration m. Of course, we know r because it's a constant, and we know T, which is 37 degrees Celsius or 310 Kelvin. So if we rearrange this equation and solve for m will equal pi over RT. Okay, so plug in pi, 7.7, divided by r, 0.0821, divided by T, which is 310. Notice that the temperature Kelvin cancels, the ATM cancels. We end up with 1 over liter over moles. So if you invert and multiply, you get moles per liter, which is molarity. So do that calculation, and you find out that a 0.3 molar glucose solution is isotonic with blood. And so that would be the concentration that you would want to get if you were in the hospital. So now there's one more thing before we move on that we have to talk about, and it's very important. So remember that colligative property means that it doesn't matter what the identity is, it just matters the concentration. Well, the concentration then depends on the number of solute particles. All right, and when we have an ionic solution, so far we've really been looking at only non-electrolytes, things that don't dissolve. But when we have an ionic solution, remember that they tend to break up into more than one particle. They dissociate. And so what happens is the actual, and so let's look at this example. So for example, when NaCl dissolves, NaCl becomes Na plus and Cl negative. Since the identity doesn't matter, just the number of particles, when NaCl dissolves in water, we've just doubled the concentration of particles. So a 1 molar NaCl solution would give me actually 2 molar of particles. And since the identity isn't important, just the number, this is something that we have to keep in mind. So actually, this is a little bit better formulas to remember for these colligative properties. For any solute that are electrolytes, we have to use these formulas, and we have to take into account how many particles that ionic compound will break apart into. And so we use the little value i, to indicate that. So our delta TF will just be little I times KF times little m, molality. Delta TB will be little I times KB times m. And then pi will equal I times mRT. So we're just multiplying by however many particles that ionic compound breaks apart into, and then we're good. So little I is the number of ions resulting from each formula. So for NaCl, little I would equal 2. if something is non-dissociating or a non-electrolyte, so if you're working on a problem and it says this is a non-electrolyte or a non-dissociating, then little I just equals 1. So you don't have to, so these equations will always work, and then if it's non-dissociating, you just stick a 1 in for I. So it's probably a little bit better to remember these equations rather than the ones we've used so far. So just you might want to go back to chapter 4 and refresh your memory. Remember that if NaCl breaks apart, you've got 2 particles. What if it's MgCl2? Well, that breaks apart into Mg2 plus 2Cl negative. So that actually gives you 3 particles. In this case, see that we're using aluminum sulfate, Al2SO4 group quantity 3. So how many particles will this break apart into? Well, since it's ionic, there's going to be 2 aluminums and 3 sulfates. So little I in this case will equal to 5. So let's find what is the freezing point of a 0.5 molal solution of aluminum sulfate. So we have to assume that little I is based on the formula, so it's going to equal 5. So Al2SO3 breaks apart into 2 Als plus 3 SO4 negative 2. So little I equals 5. Okay, so now that we know that, to find the freezing point, we're going to use the freezing depression equation. Delta TF equals I times KF times M. Since it's an aqueous solution, we're using 1.86 for water as the constant. The molality is 0.5. Whatever that answer is, we have to multiply that by 5 because the concentration of particles is 5 times as great as the concentration of the aluminum sulfate. And so the delta TF would be 4.7 degrees. Don't forget the last step. What will the actual freezing point be? This 4.7 is the freezing point depression. Since the freezing point of water is 0, the freezing point depression will be negative 4.7. The freezing point depression is 4.7. The freezing point will be negative 4.7 degrees Celsius. Right, so let's look at a problem. Which of the following solutions will have the lowest freezing point? 1 molal cobalt nitrate, 2 molal potassium chloride, or 3 molal C2H6O2, which is ethylene glycol or antifreeze. And notice that that is a non-electrolyte. So in order to figure this out, you could actually plug this in the equation and you can find out what delta TF would be because we know what KB is, or KF I should say. We know what KF is and we know the molality. But since the K is the same no matter what, we can actually just look at these concentrations and figure out which one will have the lowest freezing point if we don't need to know the actual amount. We can use some terms called osmolality, is a term where it equals little I times the molality, or osmolarity can also be used where osmolarity equals little I times molarity, capital M. In this case, I guess it was given in molality because we're talking freezing point and that's easier to use, but we know how to convert molarity to molality, etc. Anyway, osmolality is just how many particles times the molality. Osmolarity is how many particles times the molarity. So because if you don't take that little I into consideration, you would probably get the wrong answer because you would say, well, 3 molal being the highest concentration will lower it the most. But again, we have to take into account the particles and how many they break up into. So if you look at 1 molal cobalt nitrate, since cobalt nitrate has a little I of 3, it will have a 3.0 osmolality. The potassium chloride, because it breaks up into 2 particles, has a little I equals to 2. Little I equals 2, it will have a 4.0 osmolality. And then the ethylene glycol, since I equals 1, will have a 3.0 osmolality. So in fact, KCl will have the lowest freezing point in this case. So you have to, so we can use, again, osmolality or osmolarity, but you need to remember what little I is when it's an ionic equation. And often I'll try to put in if something, usually if you see a formula that you don't recognize the ions, then it's generally non-electrolyte, but I'll try to give you that if that's the case. So osmotic pressure will also depend on the number of solute particles, and so that really will have an effect, on blood cells or on solutions. So we saw earlier that the molarity of glucose, which is isotonic with cells, was found to be 3.0 molar. So if you're talking about NaCl, what molarity of salt or NaCl would you need? Well, the concentration of NaCl that's isotonic would have to be 0.15 molar because it breaks up into two particles. But you can see then, since glucose doesn't break apart, it has an osmolarity of 0.3. And because the NaCl breaks up into two parts, if you find the osmolarity, which would be 2 times 0.15, you'll get that they're the same. They have the same osmolarity, which means they have the same osmotic pressure. So again, you have to remember to consider little I in all of these equations. Just for a little FYI, if you've been in the hospital, you may say, wait, I don't recognize those concentrations at all. In clinical situations, the concentrations are expressed as a mass percent. So let me just show you those calculations. Glucose actually in the hospital is a 5.4% solution. Saline is a 0.9% solution. And if you look at that, so if you take 3.3 molar and convert that to grams per liter, and then convert that to grams per milliliter, and then multiply by 100% because percent is always grams per 100 milliliters. So there's 5.4 grams per 100 milliliters of solution, and so that's why you'll usually see 5.4% glucose. Saline, because it's 0.15 molar times the 58.4 grams per mole, and then convert that to grams per milliliter times 100% will give you a solution that's 0.88% by mass. And again, just keep in mind that because NaCl breaks apart into two particles, the osmolarity will again be 0.3 in both cases. So these will all give you isotonic solutions. All right, so one of the last things that we're going to do is to be able to determine the molar mass or molecular weight, which is the same thing, from a colligative property. We could use any of these 4 colligative properties to do this process, and in fact, one of the labs that you're likely going to do is a colligative property lab where you will find out the molecular weight of an unknown. So for example, we could measure the freezing point of a pure substance, which is in fact what we do in the lab. We use pure cyclohexane, and then make your solution and measure the freezing point of that solution. So then you can find the freezing point difference, the freezing point depression. How much will that how much will that solute lower the freezing point? So you can find delta T. Once we know delta T, then, and since we know how many grams of the solute we put in to the solvent, we can figure out we can figure out the concentration from the delta T, figure out the concentration, so that will help us figure out how many moles we have. And then because we know how many grams we've put in, we can find the grams per mole. So I think an example will make this much more clear. Okay, so here's an example. A solution of an unknown non-volatile non-electrolyte. That's important because we need to know that I equals 1 to do these kind of problems, or it has to be told to you. Anyway, a non-volatile non-electrolyte was prepared by dissolving 0.250 grams of that unknown substance in 40 grams of carbon tetrachloride, the solvent. Then the boiling point of that solution was 0.357 degrees Celsius higher than that of the pure solvent. So they're actually not telling you what the actual boiling point was of the pure solvent and what your solution is, but they're telling you that delta T B is 0.357, that it was 0.357 degrees higher. So calculate the molar mass of your unknown. All right, so first of all, since it's carbon tetrachloride as the solvent, we need to know that Kb is equal to 5.02 degrees Celsius per mole. And then we know for the boiling point elevation that this equation is true. Delta Tb equals I Kb m. Little I equals 1 because in the question it says it's a non-electrolyte. So we can ignore little I, it's just equal to 1. Delta TB was given to you in the problem. It's 0.357 degrees Celsius. So we can rearrange this equation since little I equals 1. We know what Kb is. We can solve for little m, for molality. So little m equals delta TB over Kb. Actually IKB, but I is 1. Okay, so if we do that math, we find that the concentration of our solution, because by measuring it from the delta T, is 0.0711 moles per kilogram solvent. So the concentration of when we put 0.250 grams of the substance into 40 grams of CCl4, and we found that the concentration is 0.0711 moles per kilogram. Okay, so we still have a few more things to do though. So we know that the concentration is 0.0711 moles per kilogram, but we didn't use a kilogram of our solvent. We used 40 grams of our solvent. So we have to find the actual number of moles that we added. So what we do is we take the, so we know it's 0.0711 moles per kilogram, and then we just multiply by the actual number of kilograms that we use, which is 0.040 kilograms. So you could also do a ratio if you know 0.0711 per 1 kilogram equals X moles over 0.040 kilograms, and you would solve it the same way. So we actually put in the solution 0.00284 moles. If we had a whole kilogram of CCl4, it would have been 0.0711 moles, but since we only had 40 grams, 0.04 kilograms, the number of moles is 0.00284. But now we were able to calculate how many moles would make the temperature drop that much, or temperature go up that much. And we also know that this is equivalent to 0.250 grams that we put in. So we can find the molar mass, which is grams divided by moles. 0.250 grams divided by 0.00284 moles tells us that our molecular weight is 88 grams per mole. So like I said, you can use any of the colligative properties to determine the molar mass. So, and this is a really common method for finding out the molecular weight or molar mass of really huge molecules like proteins. So let's look at this example. An aqueous solution was made by dissolving 3.5 milligrams of a protein in enough water to give 5 milliliters of solution. The osmotic pressure of the solution was found to be 1.54 torr at 25 degrees Celsius. Calculate the molar mass of the unknown. Since protein is non-dissociating, little I equals 1, so we can pretty much ignore it or we can plug 1 in. So remember that osmotic pressure equals I molarity times R times T. We have to be really careful because R is in liter atmosphere per mole Kelvin, so we're going to have to convert our pressure to atmospheres one way or another, and we have to convert our temperature to Kelvin. So we're going to be solving for concentration. So M, and here, since the units of R are atmospheres and Kelvin, we have to convert those. So first thing I did was convert torr to atmospheres. So it's 0.00197 atmosphere is the osmotic pressure. And of course the temperature is 298 Kelvin. So if we rearrange the equation, the molarity of this solution will be pi, osmotic pressure, over IRT. So 0.00197 atmospheres divided by 1 divided by 0.0821 divided by 298 Kelvin. The Kelvin will cancel. The atmospheres will cancel, and your answer will be in moles per liter. So if you do that calculation, notice that it's 8.28 times 10 to the minus fifth molarity is the concentration. Now that would be how many moles there would be in this if we had a liter of solution. So, but we don't. We have milliliters, so 5 milliliters, so we have to do a little more converting. So we want to know the absolute number of moles. not the concentration. So we multiply the molarity times the actual number of liters of solution. So 5 milliliters is 0.005 liters. And so we actually have put in 4.14 times 10 to the minus 7 moles of our unknown protein. So finally, we can figure the molecular weight, because molecular weight is grams per mole. So we know how many grams, 3.5 milligrams, and we know how many moles. We do have to convert milligrams to grams. All right, so now we know how many moles we have, and we also know how many grams. We need to convert, like I said, from milligrams to grams. So 3.5 milligrams is 0.0035 grams. So the molecular weight is grams, 0.0035 grams, divided by moles, 4.14 times 10 to the minus 7th moles. And we find the molecular weight is 8,450, or 8.45 times 10 to the 3rd grams per mole. Which is very large, and again, this is actually a very small pressures can be measured very easily, and so this is a really good way of determining molar mass of large macromolecules like proteins or polymers. So this is a really common method. Again, remember the process. The first thing we do is find the concentration by using either the change in temperature, the delta TF, or the delta TB, or in this case, the osmotic pressure. So we can solve for the concentration for each of those different equations. Generally speaking, these kind of problems, you'll either be told what little I is, or you'll be told it's a non-electrolyte, so it'd be 1. So first we find the concentration, and then we have to multiply by the actual volume given, either 5 in this case milliliters, or in the last case kilograms of solvent. And then once we find that the literal number of moles and the literal number of grams, because that's what we put in, then we can find the molecular weight. This is an example. Like I said, there's a lab that we do where we take the freezing point depression and find the molecular weight of an unknown. So hopefully before the test you'll have a chance to do that lab. All right, so what should you be able to do in this chapter? Well, you should, in general, understand the solution process. Why do some things dissolve in other things where some compounds dissolve